So in this particular problem, we have car A has a mass of 4,000 kilograms and is moving at 1 meters per second to the east, and then it collides with car B that has a mass of 2,000 kilograms moving at 8 meters per second to the west. And here's part A, B, and C. If you need to pause it, read it. Other than that, let's get going with part A. Part A wants us to find the change in momentum, or known as the impulse, of car A, or excuse me, car B, the 2,000 kilogram car. So car B is 2,000 kilogram. I boxed here just to keep your work focused there. So therefore, the change in momentum is simply calculated using final momentum minus initial, but here everything has a subscript B because we are currently looking at car B, which is 2,000 kilogram. So therefore, I can break up PFB into MB times VFB minus PIB, which is just MB times the initial velocity of car B. Here I'm just going to factor out MB. You don't have to, but I will. Therefore, it would just be MB times the change in velocity of car B. So MB being 2,000 kilograms, because that's what we are focused on. Car B being on the right here, labeled as 2,000 kilograms. VBF is 4. The diagram shows that after the collision, car B does ricochet or rebound to the right at a rate of 4 meters per second. The arrow is pointing right, so that's a positive 4. So I'm going to keep my VFB as positive 4 minus, which is part of the function here because it is change in velocity. However, I do want to point out that VIB is actually negative 8, even though the diagram shows that it's 8 meters per second pointing leftward. It did not label it as negative 8, but just because the diagram doesn't, label it for you, doesn't mean you can't do it yourself. So therefore, I want to know, well, I know that I need velocity, and therefore this particular arrow is pointing left, so I need the direction as well. So therefore, this is negative 8, not positive 8. A negative times a negative makes a positive, so there's a negative sign outside the parentheses here. This is a negative 8 meters per second because it's moving leftward or westward, whatever you want to say. Therefore, 4 plus 8 now, because a negative and a negative makes a positive, so 4 plus 8 is 12. And if you multiply this value on your calculator, you get about 20, or you get 24,000, not about, it's a perfect number here, 24,000 kilometers meters per second. And I've chosen to include the positive sign here because it did ask for change in momentum, and momentum is a vector, so I need the direction as well. Let's go ahead and move on with part B. Part B asks you to find the velocity of car A. So therefore, to find the velocity of car A, set up conservation linear momentum. Initially, you have two objects moving, so there's a PAI plus a PEI, and then on the right side, there's a PAF plus a PBF. And I'm just going to go ahead and expand PAI, PBI, PAF, and PBF into a respective term. So here, PAI is simply MA times VAI. Likewise with PBI, it's just MB times VBI. And likewise on the right side, the only difference, once again, is just a subscript F for final here. So I'm just going to plug values in. MA being 4,000 kilograms. VAI being a positive 1 because the diagram shows that car A, or truck here in this case, is moving 1 meters to the right. VB is 2,000 kilograms. Once again, be careful with signs here. VBI, even though the diagram labels at 8 meters per second, but there is an arrow pointing left, so I'm going to go ahead and put in negative 8 because in momentum, the V here is for velocity and you need the directions, okay? So make sure you pay attention to signs, otherwise you can overlook that kind of stuff and it will screw up your answer. All right, on the right side, MA is just 4,000, VAF I don't know, VB I do know, which is 4,000. VBF is given as positive 4 in the diagram, once again, because it's ricocheted to the right, and right is positive. If we clean this up a little bit, on the left side, it reduced down to negative 12,000. On the right side, we have 4,000 VAF plus 8,000. So to get VAF by itself, the first thing I need to do is move this positive 8,000 to the left. So I'm just going to go and subtract that from both sides. Therefore, I have negative 12,000 minus 8,000 equals to 4,000 VAF. I want to simplify the left side. Negative 12,000 and negative 8,000 will make negative 20,000. And then to get VAF by itself, divide both sides by 4,000. So therefore, the answer here, the final velocity of car A after the collision, in this case, it will actually move leftward. So therefore, the answer is negative 5 meters per second, and it asks for velocity, so I'm going to include that negative sign because velocity is a vector. So we say car A after collision rebounds to the left at a rate of 5 meters per second. Okay. All right. Question part C. Excuse me. Same question. Part C asks us to find or to determine if this is elastic or inelastic, and it says to justify. Well, the safest way to justify whether it's elastic or inelastic is just to check the kinetic energy of the system before and after. So I'm just going to go ahead and find the kinetic energy of the system before. So initially you have two objects moving, and Ke is here's the scalar, so I don't really care for the signs of the vectors here given the diagram. Kia, or the initial kinetic energy of car A, and the initial kinetic energy of car B is simply 1/2 mv squared, respectively, and therefore I'm just going to plug in values. 1/2 ma is 4,000, and mass A is initially moving at a rate of 1 meters per second here. VAI is just speed, so it's just 1. We're going to square that, and then likewise with the second term, MB here is 2,000. It's moving leftward at a rate of 8 meters per second, but I just need the speed here because Ke is a scalar, so I'm just going to plug in a positive 8. Then we simplify this on if we simplify this on our calculator, you get 2,000 for the first term and then 64,000 for the second term, and the sum of this will give you a value of 66,000 joules. Well, once again, now that we have KEI the system, we just find KEF the system. Similar strategy. The only difference here is the subscript F. So therefore, we have two objects moving after the collision. Here, MA is 4,000. We already found VAF in the previous work, which is 5. So even though in our previous work we found the velocity as -5 because it's moving leftward, here in KE we just need the speed, which is just the absolute value. So it's moving at a rate of 5 meters per second. We're going to square that. And then 1/2 here, MB is 2,000. And then the diagram tells us that here, I'm circling it back and forth on my cursor, after the collision, car B is moving to the right at 4 meters per second, and that is given. I don't have to do any work. We're going to square that. We're going to simplify this. So the first term is 50,000. The second term is 16,000. So if we add 50,000 plus 16,000, we'll get 66,000. So as you can see, KEI and KEF are equal. So therefore, it is an elastic collision because it fits this particular definition. In an elastic collision, momentum and KE of the system is conserved, and both of them are conserved in this particular problem. So therefore, it is an elastic collision. Okay, stay nerdy, don't be wild.